This video will introduce counting notation and how to use Venn diagrams. First, to begin with, let's define and provide some notations. At the very beginning, it says Venn diagrams, and then a way to visualize elements of sets. A Venn diagram generally has a rectangle to represent the universe, and then a circle for each set that is being looked at. And generally it's 2 or 3 sets. Now, when we want to know how many items are in a set, we use this notation n for number, and then inside the parenthesis, the set name. So here I'm using a generic S. So the number in set S. Now, we're usually looking at the number that are in a union, or the number in an intersection of 2 sets, or maybe 3 sets. Let's first begin with the union. So the notation is the number, and then in the union of S and T, and that happens to be equal to the number in S plus the number in T minus the intersection. So let's go up to this Venn diagram and utilize it to help us understand where that formula comes from. So the number in S union T, that's the 2 full circles together. So I would want to know the number in S, so that's everything in circle S. And I would also want to know the number in circle T. And we can see that these 2 circles have an overlap. So if I count S and T completely, then I end up double counting the intersections. And that is why we have this subtracting an intersection. We're leaving one of the intersections, but we're subtracting the duplicate. So that's for union. And an extra detail about union is if 2 sets are disjoint, remember that means the intersection is 0, then this formula for counting the union of S and T can be simplified to just the number in S plus the number in T. But that's only for disjoint sets. Intersection. The number in S intersection T is equal to the number in S plus the number in T minus the number in the union of S and T. This is really an adaptation of the first formula. Some textbooks don't give this second formula because it's simply an adaptation of the first one, and you can always find the intersection by using that first formula. But I find myself and other students usually liking this second formula quite a bit. There's 2 other formulas that I'm going to introduce here, and they're DeMorgan's laws. So the number in S union T and then complement. So that means everything outside of circles S and T. So for this first one, if I have a Venn diagram and I have circle S and circle T, with DeMorgan's law, S union T and then complement is everything outside of the 2 sets. With the following one, the number in S intersect T complement we now are looking at everything outside the intersection of S and T. Now S and T intersecting is right there in the middle, so we're looking at everything else. And DeMorgan's laws say that the complement of S intersect T is equal to the number in the complement of S with the union of the number in complement of T. From here, I'm going to move down and work through 2 examples. The first example, a survey of 120 people investing in stocks and bonds revealed that 90 owned stocks and 70 owned bonds. How many people owned both stocks and bonds? I'm going to begin by using the formula. And the formula, if you remember, was that if I want to know the number in stocks and bonds, that I'm looking at the number in stocks plus the number invested in bonds minus the union. And I knew that I was looking for the number of stocks intersecting with bonds because it says stocks and. Whenever we see and, that's a very good sign that this is intersection. So now I place the values in for S. The number that are in stocks only is 90. I shouldn't say stocks only. The number invested in stocks is 90. The number invested in bonds is 70. And the number invested in both stocks and bonds is 120. So I can see that this simplifies down to 40. That tells me that the number that are invested in both stocks and bonds is only 40. Okay, I'm going to use that information to build a Venn diagram. So I'll label this one stocks and this one bonds. I know the intersection is 40. Now I knew in stocks there were 90 altogether. I've already placed 40 in the large circle S. I subtract 40 from 90 and find out that 50 are stock-only investors, 40 are stock and bond investors, and then for bonds, there were a total of 70 for bonds. I've already placed 40 in this large circle for bonds, which means that leaves 30 for bonds only. Now, one thing about this particular problem is it doesn't talk about the universe, so we have to make the assumption that there's nothing outside the two sets, and so the number in the universe that's outside the two sets is 0. One more example. This is given outside of context. It says, given the number in S equals 4, the number in T equals 12, and the number in S union T equals 15, find the following. Okay, so I know S, T, and the union, and I'm trying to find the intersection. So this is similar to the last problem. I want to take the number in S plus the number in T and subtract the number in the union of S and T. This will have 4 plus 12 equals, minus 15, and that will equal 1. So the number of elements in the intersection of S and T is 1. At this point, I'm going to build a Venn diagram to place all my values. I know from that last problem that the intersection has 1. Altogether, there are 4 items in set S. I have already placed 1, which leaves 3 items that are only in set S and don't have anything in common with T. T had 12 originally. 1 has already been placed. That leaves 11 elements that are only in T and have no overlapping connection into S. I once again have to make an assumption that there's no other items to put outside the circles in our universe, so that will stay 0. Hopefully this picture will help me with part B. It says the number in S union T complement. So this uses one of DeMorgan's laws, and this would equal the number in S complement intersecting T complement. That requires us to figure out what S complement is. I'm going to draw a Venn diagram without the numbers to figure out what S complement looks like. So S complement is everything outside of S. And T complement is everything outside of T. Our challenge is to figure out where is the overlap. And I can see that the overlap of the green and red lines is everything outside of the 2 circles. So our number that represents the items outside the 2 circles was 0. For part C, I want to know the number in T complement. Well, I know altogether in this entire Venn diagram, there are 15. And I'm going to subtract out the number that are in T. So that's really the universe minus the number in T. And we have 15 minus 12, so that equals 3. And the number in S complement is the number in our universe minus the number in S. Our universe is 15, and we subtract the number in S, which was 4. So I find out that S complement has 11 elements.